Thanks, Luna. Hi, like I said, my name is Michael Salib. And so I'm going to be talking about the work I do at Indigo Ag. We're an agricultural tech company in the United States, in Boston and Memphis. And we run a carbon sequestration program where we effectively connect people who want to buy carbon credits with farmers who want to be paid to basically use regenerative practices that allow them to accumulate carbon in the soil. To do that, we have a lot of soil scientists, we have a lot of scientific validation, but our model requires extensive data, oftentimes way more data than actual farmers can provide. So we try as much as possible to augment that manual data with remote sensing data. To do that, we generate zonal summaries using a system called Viperfish. I'm the guy who came up with Viperfish, even though I work with a wonderful team now. And we take those zonal summaries, feed them into machine learning models. So what's a zonal summary? This is a common thing in remote sensing. Nobody outside of remote sensing knows about it, I believe. Remote sensing data is usually going to be georeference rasters. What that means is image files stored in the cloud somewhere with a bit of metadata that allow them to associate every single pixel in the image with a point on the surface of the earth. So you can think about satellite imagery, optical or radar. You can think about weather data, so like a map of precipitation. You can think about crop classification masks. That's the sort of thing we're dealing with. Typically, we've got a bunch of vector polygons on the surface of the earth that describe farm fields of interest or even parts of fields. And you can imagine taking your georeference rasters and just masking out the bits that match each of your vector polygons and extracting out a bag of pixels. Unfortunately, that representation is awful. It's enormous, and you end up with the shape and size of those pixel sets varies over time, even for the same polygons. And usually machine learning wants to see very fixed, consistent tensor shapes. So can't really do that. So what do? We summarize those pixel sets. We generate summary statistics for each band, and bands correspond to color and other things. And then we store that tabular data set in Apache Parquet, which is a columnar file format. Really works really well with the cloud, so you can extract just the bits you need without necessarily having to download a giant thing. And the end result of that is that summaries end up being dramatically smaller than the raw imagery and even than the bag of pixels representation. All right, so how hard could that be? It doesn't sound you just summarize some pictures, right? Yeah, it turns out operating it efficiently at scale is hard. We've got a team that has world-class experts in image segmentation, and so they've been able to develop models that allow them to take imagery and find all the cultivated fields in the world. And so even when we're just looking at the continental US, that's millions of fields, it turns out. So already the numbers start to get big, and we support probably over 24 data products. Some of those products have very high spatial resolution on less than 10 meter pixels. And some of those products have very high temporal resolution. You can think about like hourly weather. So once you start multiplying those numbers out together, you're looking at a lot of data. Most of our inputs are cloud optimized geotiffs hosted in S3. And so that introduces its own complexities. We always have to operate in the exact same region where the data is hosted. If you don't do that, the cost of transiting data, of sending data across the internet is catastrophic. We can't afford that. And of course, a lot of these data sets, especially satellite data sets, are tiled. So you'll get Sentinel-2 will be divided into these 100-kilometer blocks, 100-kilometer by 100-kilometer blocks. What happens when your polygons span a block? That's a problem. Finally, we have to be super low cost to operate when we're operating at scale for doing very large batch sets of work. And we also have to be low latency when we're doing very small chunks of work to satisfy API requests. Those are in tension. All right, so how do we do that? Well, we write a ton of Rust code. And that code runs in both AWS Lambda, which is a function as a service environment, and AWS Batch, which is a cheaper container scientific computing environment. Batch is super cheap, but has high latency. Lambda, low latency, but more expensive. Remember that problem about what happens when polygons span a tile boundary? We solve it by kind of adopting a MapReduce architecture and generating what are called T-digests. They're kind of summaries. They're distribution summaries for each band. And the nice property about them is they're compact, and you can serialize them and then merge them. So what we end up doing is a pipeline architecture that runs kind of mappers to actually fetch data, spatial reducers to collapse these, anything that's been split, and then temporal reducers to continuously join the results. All that is connected by queues. We have no persistent, when nobody's using the system, it costs nothing. So this has been really great for us, and Rust has made this way more pleasant than it otherwise would have been. I want to say thank you so much to everyone.